And give me just one moment. Okay, linked lists. They are a little more complex. They're a series of nodes, right? And we saw this a little bit on Monday. And linked lists, and then when we look at trees a bit tomorrow, this is where, and everyone can see my screen, correct? And it says linked lists, and there's like a diagram. Perfect. It starts to get a little more complex because stacks and queues, it's basically we use like a list or an array, and we write a wrapper around it. And it's relatively straightforward. But here, like this data structure gets a little more complex because we're creating a thing that holds the data and information about the next thing in our data structure. We can't just necessarily use a list to keep track of all this stuff. And if you remember talking about memory on day one and sort of arrays and stuff, again, the context here is like sort of like at a low level in the computer. If I've downloaded a movie to watch, that's a really big file. The computer is not going to be able to put that like in hard drive storage in like a continuous block of memory. Like one chunk is going to have to be in one part of memory, another chunk somewhere else, and so on and so on. And there's a bunch of different ways to keep track of that. And one way, honestly, is maybe the computer then just has a list of like, this is the address of chunk one, this is the address of chunk two, and so on. Another way to do it is where each chunk holds a pointer to the next bit. And there's pros and cons to be made for both cases, but that's really where like a linked list comes from. And you can use it to build like all sorts of interesting things. And as you can see, there's basically two bits. There's really three things here to think about. We've got nodes, and we're going to use a class. You could use a dictionary. It's a little easier, I think, with a class. And each node needs to hold some data and point to the next item in the list. How is my internet, by the way? How is like my voice?
You lagged pretty bad there. I was like 10, 15 seconds, I think. You stopped talking on my end.
Mine too.
Okay, sorry about that. How are we now? Are we doing okay?
It's good now, yeah. It kind of fixed itself. It was like one little stutter.
Yeah, I got that little your internet connection is unstable sign. Please let me know if that happens again, because I might miss the little warning. And I can always go off video, or I don't know, make sure I don't have something else going on. My home internet is pretty good, but there's always something
Could could you repeat yourself? I think you left off from like there's like three things in this.
yeah, totally. Yeah, there's basically three things. We're gonna so this term node is one of these catch-all terms that we're gonna see pop up again with trees. No pun intended. And so like the same way we'll talk about items or elements in a list or an array, we'll talk about nodes in a linked list. And so we're going to create a node class, and that has to hold the data in each bit of the list and a pointer to the next bit of the list. And then the other thing we need is, because the only way to get to the next node in a linked list is from the previous one, we do have to hold on to the very first item in the list, the head of the list. And I think this is sort of what Frank was touching on earlier, is that like with lists, there's a common terminology too of head and tail, where the head is the beginning of the list and the tail is the end. Because if we have the first thing in our linked list, the first node, the head, we have the pointer to get to the next and so on, and we can go to every link of the chain. If we don't have this though, then it doesn't work. So we always have to have this. And this is what I'm about to implement, and then we can kind of see it. And really, all of the more challenging assignments for today are sort of variations on stuff to do with linked lists, because that's where it starts to get trickier. So at a minimum, we have to be able to insert, we have to be able to add something to the beginning of a linked list. Or again, as we saw with the queue, we could do different implementations. We could have a linked list where things start at the end. And we need to have some sort of search to go through the list to find what we want. Removing something from the linked list is also common. That is a little bit trickier, and that's actually one of the assignments or stretch assignments for today. So we're just going to focus on inserting, and then if we have time, we might do a little bit of searching. So I think what I'll do is I'll just maybe talk through this, and then we'll code it. Does that sound good to folks? Cool. So we're going to create a class named node, right? And each of these is going to be an instance of the node class. So unlike a stack or a queue where we created a class that we created like a my stack instance or a my queue instance, and there was just one, with a linked list, we're going to be creating like multiple instances. And don't worry too much about coding along yet. I'll be typing it out in a minute. So if you want to, you can, but I'm going to move more at an explanatory pace. And then I'll code it up in a minute. When we initialize this node, we do want to pass in the value. So that's the data that we're going to hold in this node of the linked list. And then we'll write a method later to like connect this to the next thing in the list. And we're going to set it to none because for the very first node in our linked list for the head, there won't be a neighbor. I guess we are going to create I honestly, I sometimes just write these as functions. It's not the worst thing to write this as a class. So we're going to make a second class linked list, and we're going to use this to manage our nodes. So we're going to have we're going to create a linked list class, and we'll create like one instance of it, my linked list, but then it'll be using that node class. And I am tempted to start adding code here because we are starting to add stuff on. Would people like me to start writing code and running it, or maybe finishing walking through the slides? Is there a preference?
I think either way is good if we're going to run the code afterward, but really that's the way that I personally internalize it, regardless.
Yeah. Okay. Let's just do it. Let's just start writing some code right now then. And for learning purposes, I'm not going to worry about like putting classes in separate files or anything like that. How's this font size for everyone? Good. So we've got a node class. And I'm going to get rid of the type annotation, though Python type annotations are awesome. And I'm not going to worry too much about the underscores or anything like that. I'm just going to keep it very simple for learning purposes. And let's see, what does this look like? Oh, there's a trailing space. And I think I saw there was a comment. Derek, I'm looking at what you're saying. So Derek, you raised a good point about the terminology for linked lists to be a little confusing. I would say, you know, for now, if when you're writing it, if it makes it easier to use your own terms, go for it. Just be aware of the common terminology. Like for learning purposes, if calling it like a link and like next link and previous link helps, then I think that then go for it. I'll probably use the term node, and I'll use it a bit too when we talk about trees. I sometimes just end up calling things like elements or items. So yeah, I don't think it's a huge deal right now, especially because our goal is to really learn and get comfortable with this. But yeah, it's a great question.
So out in the wild, do most engineers pretty much stick to the commonly understood terms when they're writing?
Probably yes. I'm honestly not sure because you really honestly don't implement linked lists all that often. That said, if I was implementing a linked list, like for example, if I was implementing a queue for like Domino's pizza ordering, I might start naming things about pizza so that like the names have like meaning in the real world context, like for the business problem. So, you know, I don't know if this was a linked list of like movie images, you know, I might just call this like movie image or something. But it depends. Linked list, sort of, I don't know what to call this, sort of like handler main class. And I actually do want to look back at this as a reference. So right now we're not doing much here. We know we need to keep track of the head of the list, and that's what we're going to do here. And we're just going to create empty insert and search methods. I do have to go ahead and add self in here. And we'll add insert. And we'll add search self. I guess I should use node for consistency. Let's see, what do we use here? Value. Oh yeah. Insert value as new node into list. I think the important thing is just to be, if you're going to focus on anything, be whatever terminology you use, just try to be consistent with it in your own code, because I think that's the biggest thing in terms of making it easy for you to see it and easier to read your code and for other people as well. So nothing fancy. We've got a node, we've got a linked list. In the spirit of running code, I will just create a node with a hello world message, and we'll just print test node value out there. We might as well just print test node next, just for the heck of it, to sort of follow the spirit of TDD. And then we'll make a list, and it has nothing. And we'll print my lists dot head, and that should be none. So we're going to see a whole lot of nothing when we run this, but at least now I know I don't have any typos in like my sort of skeleton code. And perfect. Hello world, none, and none. Exactly what I wanted to see. And now I can go on and build with this, and I know I don't have like a typo or anything lurking to trip me up as I start doing more complex stuff. So we do have a choice to make when we create a linked list of basically where do we insert something. So here we're going to choose to insert at the beginning of the list, we're going to set the head to none. The challenge with the linked list is always to know when are we at the end. And what we're going to do is when we're at the end of the list, the next node will be none. So in fact, I'm going to write this down somewhere. And I think I'll just write it down maybe here in this comment, this main doc string here. Insert at head of list. If next, if node dot next is none, it means we are at the end of the list. So this is sort of a shorthand, but I'm saying, hey, if some node in the linked list, if its next value is none, that tells us we're at the end of the list. Right, and to kind of go back to this diagram, this is what we're going to do, where we've created this node class for each of these. We're going to connect them to each other. When I hit a node where next equals none, that tells me I'm at the end of the list. Do folks have questions, thoughts, things like me to go over again? Matt, good question. I think it'll be easier to see it when we implement it, about sort of what is self.next or self.head. I think it'll be easier to, it'll be a lot easier to just implement it and see. So we have to do a little bit of work here to insert a node. And this is sort of like the classic bit that I think is a little tricky to think about. And this insert method is doing a couple things. First of all, note that the argument we pass it is not a node. It's a value, right? It's the actual information that we want to store. And the insert method does the work of creating a new node. So this is where we're going to use our node class. And we're going to create a new node with the value that we want. And now we have to do a little bit of dancing, because we are inserting at the beginning of the list. So we need to end up with, so to kind of go back, and this is where I have the iPad, but it wasn't set up. Like when we're adding something new to the linked list, we're not sticking it here. We're sticking it here. So I wonder if, actually, let's see what we can do here. Maybe we can use the, maybe we can use the Zoom whiteboard briefly, and it can have its like moment in the sun. Because this is, I think, the part that people get hung up on a lot. So I'd rather kind of diagram it and walk through it. Okay, let's see how this goes. Let me go ahead and stop sharing my screen and see if I can't make a whiteboard here. I will make this a collaborative whiteboard, but please don't go wild just because I want to draw some stuff on it. Awesome. In fact, I'll just sign in so we don't lose it. Yeah, feel free to have fun. Just try to keep the space in the middle relatively clear. So I've got some nodes in my linked list, right? Let's say we've got this one here. And now that I've got the pencil here, A, and it points to B. which points to. And how is this drawing, by the way, in terms of like, can everyone see that? Is everyone able to scroll to see this in the center of your screen? And if someone cannot see me writing A, B, and C here, please let me know, so I know. Everyone can see this A, B, C, and none? Awesome. So right now, that's the head of our list. For my insert function, remember, like what we're doing for insert is, first, new node equals node value old node equals self.head. I'm just going to write this out and then we're going to diagram it out. That should be a dot. Let's see if this eraser does its thing. Not quite. I'll have to figure out erasing another day. Right, so this is the code that we're going to implement for our insert node method. And forgive that this is terribly scratchy. But so off over here, and I think I'll just kind of put it over here. We've got our new node. And we'll have the new node be red, right? So that's our new node. Can everyone see that? Okay. Awesome. So we've created it, we've given it the value X, but we haven't done anything with it yet. And the key thing to remember here is that we insert at head of list. That this is our strategy for implementing a linked list. We can do it either way. We can insert at the head, or we can insert at the end of the list, at the table, at the tail. We want to insert at the head. So I need to do two things here. I need to not lose track of the old head. So right here, this line of code, old node equals self.head. That's because I don't want to lose track of the current existing head. Because if I lose track of that entirely, then I can't access the rest of the list. So I kind of need to do like, I need to create another variable and point it to that same thing. Then I can change the value of self.head, and this is in the linked list class. Remember, this is all happening inside our linked list class, to the new node. And let me find the eraser here. That would not be it. That would not be it. It has got to be somewhere around here somewhere. Actually, if anyone knows, please do tell me, because I would have thought this was a little more obvious. Ah, I think I found it. There we go. So for our linked list, self.head is going to point to, and let's see, was that in black? We'll use blue, maybe. We'll use blue. That is a terrible arrow. In fact, let me just go ahead and erase it. This is trickier than one thinks. So this is an experiment. Anyway, terrible arrow. And for some reason, oh, that would be why I was drawing shapes. Lord knows why. So ignore all of those triangles and actually really nice looking arrows that some really clever zoom thing I didn't mean to use did. But the point being, we've now set self.head equal to the new node, line 3, right here. But we've still got the old node because we've got it set there. So now what we do is this self.head.next. Well, this is our new node. That's now our new node. And we set its next to point to the old one. So I hope that this whiteboard helped as much as it hurt, but that is sort of like the walkthrough of visually speaking, like the replacement process. There's a couple extra things there along the way. Unfortunately with Zoom, I have to close the whiteboard to screen share. So before I close this to then like write this code and run it, what questions do people have? I would love to like get to the point where like someone can come up to the whiteboard and draw stuff. But to be honest, I think with my current state of Zoom whiteboard knowledge, that will be more time consuming than beneficial. So as long as we're looking at this, what questions do people have? Matt, yes, sir.
So is this example just like the most basic example where it's like all you have is the head and or like the value and the next node? So like more practical examples, you can actually put more data in there, or is it like this is it? It's kind of
So-
just like used for a pointer.
This is an example of, so in the example, I guess I did add like B and C already, like, so I kind of added some stuff. What I just walked through is how we would add the very first node to our linked list, how we would add the second node to our linked list, and how we would add the third node, the fourth node, and so on. The very first time is a little funky, but because there's nothing else, it works fine. But then like every time we want to insert a node, this is what we do.
I mean like each node itself, could it have more data attached to it where it's like you can just have, I don't know, whatever your program's doing, you just, that's where all the data would be. And then it's just, if you want to store it in a linked list format, it just always has to be like a head, like have a value and then a next node pretty much.
Each node we can put whatever we wanted there. I just put those like A, B, C, and X. Those were meant to be like the characters A, B, C,
Gotcha.
like a string or
Okay,
whatever.
okay.
Yeah. Sorry for that confusion. Does that help a little bit?
Yeah, I think it's more like, I think I'm just confused, like argument wise, like, can you have just a bunch of data in there? You could have like 40 other like self dot name, self dot, you know, first name, last name, like just weird arbitrary data like that.
I see. You could, but you would not want to. What you want to do is the node really is a wrapper. if I have like some complex stuff, like for instance, if we had a user account with first name and last name, maybe the value that I pass it is that dictionary, or maybe I have a user class and I pass it an instance of a user class and I set it to node.value. The node class I want to keep pretty sparse and as a wrapper, and it's really just for like moving through the linked lists and stuff. So if I want to stick something in my node data that's more complex, then I would use a dictionary or some other class instance and just assign that to self.value in the node.
Okay, got you. Thank you.
Yeah, great question. Great question. Does that make sense?
That makes way more sense to think of it as like almost like a container for other data types that we're working with to make it easier for us to manage moving it around and like knowing what I guess what it is or
That is exactly
what
how to
goes with
think
what.
about it. Yeah, that's actually a great metaphor. Like each node is like a container, like each node is a bucket. In fact, I'll just draw some terrible buckets here. And we can fill it with water or orange juice or ice cream. Maybe because I'm sick, I'm only thinking of liquids. But we can put whatever we want in the bucket, but the bucket's job is really just to hold the stuff. And going back to when I was kind of going like off the deep end, talking about like an interface and API, like application programming interface, that's really like the interface that we want to keep for our node, like for the shape is like you've got value and you've got next, and that's the node's job. And there is something called the single responsibility principle. That's like one of these sort of best practices for object-oriented programming, where, and just in general with programming, you kind of want to have everything do one specific job. Like it's better to have a function do one specific thing than like a dozen of big things. People break the rule all the time because sometimes it's easier to just have one big function, but it is a good way to think about stuff and thinking about like what parts of my program have what different jobs. And as we design more of this stuff, I do think it helps to think about and keep stuff a bit more specific. So like the node's job is to hold whatever we want to put in the bucket and point to the next node. Yeah, great question. What other questions do people have before we close the diagram? Oh, Brian, great question. Is the way that Git commits are logged an example of a linked list? It very well might be. It's definitely something along these lines. I'd have to look it up specifically. But that's a great question, and you're thinking along the right lines. I can actually Google that. The internet says it's more correct to say that it's a directed graph. And it's not worth going into, like linked lists, graphs, trees, it all gets a little fuzzy. I'm not sure off the top of my head, but you're thinking along the right lines. Any other questions, comments, requests for illustration before I kill this whiteboard?
So can you only like connect in one direction? Or it's like could at B could you then make another connection going like up or down to another node and start branching off?
Great question. At that point, you are now building a graph or a tree. And we wouldn't call it a linked list. You totally can. In fact, people sometimes do doubly linked lists where you can go backwards. So you've got arrows pointing in both directions. So you've got a singly linked list, which is what we see here. A doubly linked list, which is more advanced, which would have arrows going in the other direction as well. Once you go beyond that, and you're not just going like forwards and backwards, at that point, you're making either a graph or a tree. But it uses all these same concepts and techniques. And yeah, Andrew, I will try to come back with some concrete examples of linked lists. There aren't always great ones off the top of my head, but it is useful to think if I wanted to build a tree data structure for, say, like a file system, which is a tree, or a graph for like Git commits, that is the same basic idea, but with more arrows, right? If I start doing stuff like this, now it's not a linked list, it's a tree. So linked lists are sort of like a stepping stone to trees and graphs and stuff. Okay. Awesome. I do have to kill the whiteboard, unfortunately, because I do want to finish implementing and running our code. So the whiteboard is going away. And maybe one of these days we'll figure out how to have both happen at the same time, which would be great. But I do want to get this working. And can everyone see my screen right now with the linked list class and code? Awesome. And let's see if I can't collapse the doc string. Good. So I just copied this in the interest of time. But we just kind of walked through what happened. Remember, we have to keep track of the old head. And here, point new head to old head to add our new node to the head getting of this. So the search, I don't think we'll have time to implement. It is, I'll do it maybe very quickly. I think I'll comment that stuff out. Let's go ahead and add some things here. And as to that great question about what can we put in there, we can put anything we want in the list. You would normally probably have like the same type of thing in a linked list, but just sort of for purposes of demonstration here. And I'm just going to do a print statement of my list. Oh, of course we can't even do that. Well, let's do head. Let's look at the head of the list and we just put one thing in there. So great. Not that interesting because I added a dictionary. And because the node, I should probably add a dunder string method here. I think it should look something like this. If anyone knows if I'm getting this wrong, let me know. Let's see if that works. No, it does not. It does not like that. And it gets a little confused because I'm adding non-string values and it's getting a little complicated. So this is where things do get a little funky in terms of printing stuff and just making sure everything is right. There probably is a nicer way to do this that I'm just not remembering off the top of my head.
Would you want to just F string it?
Sorry?
Just F string it so that you have what you put already in your string method just in curly brackets.
That's not a bad idea. I don't know if that will really work. Let's see here. Ah, great call. Thank you. Beautiful. So for the node, this dunder string method, when an instance of this class gets turned into a string, like if say I want to print it, Python looks for a dunder string method, and if it doesn't exist, that's why it prints out that whole like just information about the class instance. And that was a great call to, because I don't know what this value is going to be. Let's just F string it and let Python do its work, because the dictionary class does have a dunder string method. Let's go ahead and add this hello world and see if that works. So now that's added now too, which is great. But of course, what if I want to see everything in the list? So in fact, even before search, what might be useful is just, how about print all items in list? And let's just do something really simple, like current equals self dot head. I always get a little confused here because we either usually use a while loop or something recursive. While self dot head is not none. Print current, and actually this needs to be current, not self dot head, excuse me. Current dot next is not none. And this is where it gets a little tricky because this is not quite right. I don't think I'm going to get the last item in the list. I always get a little screwed up with this, but let's see how well we do. Right, so we have to tell the list to go look at for the next thing. As I said, I don't think this is going to print everything. Let's add a third thing just so we have enough to see what's going on. And let's do my list, all items in list, and see how well we do. So I added 3 items to the list, but I've only seen 2. And I wonder what's going on here. If I made a mistake or what. I think the easiest thing to do is first, since I've only got 3 things in the list, let's just do this self dot head dot value, excuse me, my list dot head dot value. Then let's do my list dot head dot next dot value, and then let's do my list dot head dot next dot next. And this would be a little ridiculous. We obviously don't want to do this for like more than 3, but as a way to very quickly just check, hey, did I properly construct my linked list? It is not the worst. So the list looks great. We're inserting in the beginning, which I honestly did forget, and it threw me for a bit of a loop. Okay, so if I run this print all items and lists, I only get 2. I only get the first 2 things. Can anyone tell me why I don't get the third one, the last one?
Because its next is none, so it's not going to display that one.
Yeah, exactly. In fact, if I use the debugger, we can kind of see what's happening. So if I step through this in the debugger, let's see, really current dot next is what we're interested in here. So we're looking at hello world. This may not be as useful as I thought. Yeah, I apologize. I'm less familiar with the debugger, but in essence, we start up, we get to the first one, we're fine, we print it out, we send current to the second one. The second item in the list still points to the third, so we're good. We go into the loop, we print it, we set the second item to the third and last one in the list. That one doesn't have next. So then the loop exits before we even print. And I kind of knew I was making this mistake as I made it, because I always make this mistake. And can anyone help me to fix it, maybe? So that we print out all three things.
Return self.head at the end.
We could do return self.head. Well, it wouldn't be self.head, it would be because self.head never changes. But I think you might be thinking of return current.
Could you put after the while loop print current dot next?
I think that would work. I think we would want current dot value, but I get what you're saying. Let's see how we do there. Ideally, we really want the loop to iterate through everything, but that does work. And honestly, that will always work. So that is not the worst way to do it, right? So we start with goodbye, which is the head of the linked list. We set that to current. Goodbye indeed points to the next thing in the list. So it's that current dot next is at none. So we print out goodbye. Then we set current to the next thing in our list, which is hello world. Then we go up here. Hello world points to one more thing in the list. So current dot next is not none. So we print that out. We set hello world to our dictionary. And here, that's the last thing in the list. So current dot next is none. So the loop exits before we print. And then here with this one more print statement, we're printing the value of current, which is the last thing in the list. So we get all three of them. So that totally works. Can anyone maybe suggest a way to modify the loop so it loops through everything?
I don't think that we should do dot next. I think that's what's messing it up. I'm not 100% sure, but I'm pretty sure if we did, if we are trying to print them all, if we just did like while self dot head and then like a semicolon, and then you just print self dot head, and then you change self dot, or you change your self dot head to equal like self dot head dot next.
Yeah, I think you got it. The only thing is that we never actually change self dot head. That is always going to be the first thing in our list, but we are
Whereas, like,
changing current.
yeah, sorry.
It works perfectly for that. No, that's awesome, Kate. Yeah, I think you hit the nail on the head there. Like,
You know the code you have right now, run.
yeah, I
Correct.
think this will run perfectly well. And we should see an extra print statement, in fact. Oh, let me in fact get rid of this because we don't see an extra print statement. We in fact see an error. Yeah, and this runs great. And yeah, Kate, you hit the nail on the head there, because you're saying, hey, let's not worry about like the next node. Like when I get to the end of the list, at the end of the list, current dot next is none. So then current is set to none. So we can just let this loop through, and we can, when we get to the end, we can just set current to none, and then we can just check for that in the while loop. And we can do that. I don't think we necessarily need the is not none. I think you're right, Kate, that this works fine. I always like being a little explicit in my loops of exactly what I do or don't want to see, but it doesn't really make a big difference either way. You'll hear people argue for either way. And now this works great, and this loops through the loop. And this is the bit that's a little tricky with linked lists, But once you kind of wrap your head around this bit, that's kind of right, the inserting and the looping to the end. Searching is really just a variation on this. So I think this is a great exercise for all of you to do in the afternoon. So we ran a bit long. Hopefully this was interesting though and enjoyable. And before we wrap, I just want to see what questions folks have about sort of like implementing the linked lists and stuff. And this is usually the trickiest one. So please fire away.
Can I see your Dunder method?
The Dunder string method up here.
Yes.
Yeah, and I'll push all this code right after this so that everyone can have it. Okay, so I think the real question is, I know this was a long class. I haven't been able to sort of fit in the hands-on work time the same way that Francisco was. How are we feeling about like implementing this ourselves and then working on and adding a, like, say, a search feature? I will take that as quiet excitement. All right. I think, oh, I see something in the chat. Yeah, the linked list that's what this afternoon is for practice. And really the task is pretty much to implement what we walked through here, and add in that search feature. And what I recommend is look at the assignment, look at the curriculum notes, because that's what I use for the slide deck. Write out like a little task list for yourself. Feel free to use my code as a guide code, but don't copy and paste it. Try to get as far as you can, and try to get as far as you can without like rewatching and following along the video, because it sort of forces your brain to recall what you've learned. And then when you hit a sticking point, try reaching out to like another student or TA. And then if you feel like I need to look at this more or no one's available, then take a look at the video. And I will make sure the videos go up right up, because I know I was a bit late in that. So they'll definitely be there as a resource. I know it feels like a bit much, but I think actually once you start coding it and implementing it and like maybe taking a piece of paper and doing a little drawing, you'll find that the pieces start to click. So that's really the plan for this afternoon. We have stand down at the normal time.